Welcome back to another explainer. I am so incredibly excited to have you here today because we're about to go on a truly mind-bending journey. We're going to travel back through 4.6 billion years of deep time to answer one of the most fundamental questions of our entire existence. How did we get here? And more specifically, how did the very ground we're standing on actually come to be?
Okay, so picture this for a second. You're floating in the deep, quiet, entirely empty darkness of space. And you look down at where our beautiful blue and green home should be, but instead of oceans and continents, you see this, a terrifying, lifeless ball of boiling lava. Just a homogeneous sea of magma, glowing red in the dark void, with absolutely zero signs of life anywhere. That was our Earth 4 billion years ago. It's kind of hard to wrap your head around, right? So, the crucial point we need to figure out is the exact sequence of events that took us from that absolute chaos to the highly organized, life-sustaining world we know today. I mean, where did all the water come from? How do we even get a moon? How did a giant sea of lava turn into solid ground? Okay, let's dive right into this. Today, we are following a 6-part roadmap. We'll start with the birth of our solar system, how dust became protoplanets, surviving the Hadean Eon, the formation of Earth's deep layers, the dramatic giant impact hypothesis, and finally, the precise recipe for life.
Starting with Section 1, the birth of our solar system. Before our planets existed, our cosmic neighborhood was basically just a massive, quiet cloud of dust and gas called the solar nebula. But then, a nearby dying star exploded in a supernova. The intense shockwaves from that blast caused the gas and dust to collapse inward, spinning and flattening out into a rotating disk.
And you really have to pause and think about the sheer scale of what happened next. As that disk spun, the center skyrocketed to 15 million degrees Celsius, triggering nuclear fusion. Bam, our sun was born. And in that process, the sun actually sucked up a staggering 99.8% of all the matter in that solar nebula. Every single planet, asteroid, and comet out there, they all formed from a tiny, leftover sliver of just 0.2%.
Before we zoom into how that tiny 0.2% actually became planets, let's anchor ourselves in time. We are literally talking about oceans of time here. The nebula collapsed 4.6 billion years ago. The incredibly violent Hadean Eon followed for the next 600 million years. And then came the Archean Eon, where Earth really started to take shape, which lasted for another 1.5 billion years. Which brings us to Section 2, from dust to protoplanets. So inside that flattened disk, that leftover 0.2% of dust began swirling around the newly born sun. And thanks to static and chemical forces, those tiny microscopic specks just started sticking together.
Scientists have a specific name for this process: accretion. It's simply the coming together of matter under the influence of gravity to form larger bodies. A Soviet astronomer named Viktor Safonov actually first proposed this theory back in 1969, and today we know for a fact that it's true. We actually find these ancient microscopic rocks called chondrules inside meteorites, and they contain radioactive uranium that formed in a supernova over 6 billion years ago. They are literally the ultimate proof of this slow accumulation process. Small clusters became rocks, those rocks became kilometer-wide planetesimals, and those planetesimals eventually formed protoplanets.
But as you can probably guess, things were definitely far from peaceful. Welcome to Section 3, the hellish Hadean Eon. Early Earth was just constantly colliding with other protoplanets. And these weren't little fender benders. These were apocalyptic impacts, generating so much heat that all the rocks melted into a sea of lava. It's absolutely no wonder scientists named this eon after Hades, the Greek god of the underworld. It was a literal hellscape, just getting bombarded by objects up to 200 kilometers wide.
But here is the totally incredible irony of the Hadean Eon. This violent, horrific bombardment is actually the very reason we are alive today. Those comets and asteroids smashing into the magma, they weren't just made of dry rock. They contained microscopic ice crystals carried over from the original solar nebula. When they hit the Earth, that water vaporized into steam, filled the atmosphere, and eventually rained down. This hellish bombardment was literally a cosmic water delivery system.
As that bombardment finally started to slow down, we entered the Archean Eon. This is Section 4, forming Earth's deep layers. By the end of the Hadean Eon, Earth was essentially just one big uniform ball of magma. But over millions of years, it began to literally organize itself from the inside out through a process called differentiation.
Think of differentiation a bit like pouring water through sand, right? Gravity is doing all the heavy lifting. Incredibly heavy metals, specifically iron and nickel, were relentlessly pulled down toward the center of the planet. Meanwhile, lighter elements like oxygen, silicon, and aluminum floated up toward the surface, and they eventually cooled to become the solid crust that we walk on today.
Let's look at the incredible internal structure this created. You know, we usually just hear about the crust, mantle, and core, but Earth actually has 5 distinct physical layers. Up top is the rigid lithosphere, broken into tectonic plates that give us our earthquakes and volcanoes. Just below that is the asteroid, this constantly moving layer that acts like a planetary lubricant. Then you've got the massive 3,000-kilometer-thick mesospheric mantle, packed with high-pressure minerals and radioactive elements like uranium and thorium that help keep the center of the Earth at a blistering 6,000 degrees Celsius. And finally, the 2 parts of the core.
This core structure builds our ultimate planetary defense system. It's divided into 2 parts, and the difference between them is vital. The outer core is made of liquid, churning iron, and because iron conducts electricity, that churning generates massive electrical currents that shoot out and create Earth's magnetic field. That field is our invisible shield against deadly solar winds. Then you have the inner core. Even though it's 6,000 degrees, which is hot enough to easily melt iron, the crushing gravitational pressure down there is just so intense that the iron is forced into a solid state.
So the Earth is formed, it's neatly layered, and it has a magnetic shield. But wait, what about the Moon? Let's get into Section 5, the giant impact hypothesis. For a really long time, scientists debated where the Moon came from. Did Earth's gravity just catch a passing rock? Did they form at the exact same time, side by side? Well, the answers to those theories turned out to be no. The reality is so much more dramatic. About 4.5 billion years ago, another protoplanet about the size of Mars, named Theia, was actually sharing our orbit. Theia smashed directly into a young, lava-covered Earth in an unimaginably horrific collision. The heavy, iron-rich cores of both Earth and Theia completely fused together, which, by the way, is exactly why Earth has such a massively dense iron core today. The remaining molten rock and debris from the impact blasted into space, got caught in Earth's gravity, and eventually clumped together to form the Moon. And the wildest part? We know this is true because when the Apollo missions brought back basaltic rocks from the Moon, their oxygen isotopes perfectly matched the rocks right here on Earth.
But that collision didn't just give us a beautiful glowing orb in the night sky. Theia hit us so incredibly hard that it permanently knocked the Earth off its axis by exactly 23.5 degrees. That specific rotational tilt is the very reason we have the changing of the seasons. Furthermore, the gravitational pull from our brand new Moon created oceanic tides, which ended up being absolutely crucial for eventually coaxing primitive life from the oceans onto the land. Which perfectly brings us to our final stop, Section 6, the recipe for life. Way back in the Archean Eon, massive volcanic eruptions filled the atmosphere with pretty toxic levels of carbon dioxide, methane, and ammonia. But as the Earth's surface slowly started to cool, all that water vapor delivered by the asteroids finally condensed. It literally rained for millions of years, creating our massive oceans. And those oceans did something completely vital. They absorbed that toxic carbon dioxide, stabilizing the climate and paving the way for rising oxygen levels. When you look at the preconditions for life, the margins of error are just terrifyingly slim. Look at these highly specific factors. We are the exact perfect distance from the sun. Our size provides the precise amount of gravity needed to hold on to a life-giving atmosphere. Our churning iron core gives us a magnetic field that deflects lethal radiation. And our volcanic activity provided just enough of a greenhouse effect to keep us warm. Literally, if that greenhouse effect had been even slightly stronger, we'd be a boiling, toxic hellscape like Venus right now. And if it had been slightly weaker, we'd be a freezing, barren wasteland like Mars. It really is staggering when you put the whole picture together. A nearby supernova, a 0.2% dust remnant, a cosmic water delivery via asteroid bombardment, a Mars-sized planet crashing into us to give us seasons and tides, and a perfectly balanced internal iron core. Literally everything that happened over those 4.6 billion years was exceptionally rare and incredibly fantastic. So I want to leave you with this question to chew on. Considering this miraculous, chaotic sequence of events required just to make Earth habitable, what is our duty to protect this wonderful, one-of-a-kind planet? Think about that the next time you look up at the moon or down at the soil. Thank you so much for exploring with me today, and I'll catch you on the next